Hello everyone. Today this is Sandeep. Today we are going to cover one of the most important topics of design and analysis of algorithms, that is asymptotic notations. First of all, what do you mean by the term asymptotic? Asymptotic literally means approximate. That is, what is the approximate time taken and what is the approximate other resource, say for example space taken by the algorithm to get executed. Just reading out the first point, that is asymptotic complexity is used to express the running time of an algorithm as a function of input size n. I say that the time complexity of the algorithm is theta of n. What does it mean? N means n to the power 1. N to the power 1 means linear. Linear means that if the size input is multiplied by 2, the time taken by the algorithm to generate the result will also be multiplied by 2. It may not be exactly 2, but it will approximately be 2. Since it is approximation, that is why this has been termed asymptotic. Next point, it is expressed only using the highest order term in the expression for the exact running time. For example, if the running time is 4n square plus 10n minus 9, then the running time will be represented as theta n square. Now, as we shall discuss, we shall count the frequency of execution of each and every statement in the algorithm, and then we shall add all the terms. So we shall get a polynomial, like this polynomial 4n square plus 10n minus 9. We shall get a polynomial. Now, each polynomial will have a degree. In this case, the degree of the polynomial is 2. Since it is 2, so the complexity will get on to be theta n to the power 2. Now, what this theta means, we shall discuss next. There are basically 5 asymptotic notations. Today we shall be covering only 3. That is theta notation, big O notation, and big omega notation. These notations describe the rate of growth of relation between the defining function and the defined set of functions. That is, we will compare that whether each function describes the upper bound of the other, or it describes the lower bound of the other, or it describes the time bound of the other. Depending on that, the relation will be either theta or big O or omega. For example, if x is any asymptotic notation, that fn equal to x of n square, then it means that what is the rate of growth as compared to the growth of n square? Whether n square rate of growth of n square is lesser than fn, or it is approximately equal to that of fn, or it will always be lesser or greater than that of fn. Depending on that, the relation will be either theta or big O or omega. Now, the very first notation, that is theta notation. Firstly, reading out the technical definition of theta gn. Theta gn equal to fn such that this is existential quantifier. Existential quantifier, it means that there exists some values. The condition may not be true for all values, but there exist some values. Just reading out, theta of gn equal to fn such that there exists the positive constant c1, c2, and n naught, such that for all values of n greater than equal to n naught, we have that c1 gn less than equal to fn less than equal to c2 gn, and all values are non-negative. That is, fn will always be lying between c1 gn and c2 gn. If you have a look on the graph, if you have a look, that fn, although in the beginning they are crossing each other, one may be less, the other may be greater, one after the other, but after the value of n crosses n naught, after that the value of fn is always lying between c1 gn and c2 gn. c1 gn is always lesser than the value of fn, and that of c2 gn is always greater than that. So we can say that c1 gn is acting as the lower bound of fn because fn cannot get less than that, and similarly c2 gn is acting as the upper bound of fn because fn cannot get out to be greater than that. So fn has been bound from both upper end as well as lower end in the theta notation. That is why theta notation is also known as tight bound. So if fn is theta of gn, then gn is the tight bound of fn. Just reading out the next point, that we say that fn belongs to theta of gn. Why so? Because it is not you can say unique. There can be multiple values of fn such that fn equal to theta of gn. There could be multiple. So that is why it is belongs to instead of just equal. Similarly, the next point is that it is asymptotically tight bound because it is acting as upper bound also, gn is acting as upper bound also, and as lower bound also for one value of c or the other for the function fn. Now discussing some examples. Sorry. The first example, that is 10n square plus 10n plus 10. Now what is, if I want to calculate that, what is the theta notation of this function? Then as you can have a look, that if I say that it is equal to theta n square, what do I have to prove? If I have to say that it is equal to theta n square, I have to find the values of C1 and C2 such that for C1 n square is always lesser than the function fn, and another C, that is C2, such that C2 n square is always greater than that. Now in this case, if you have a look, if I take C1 equal to 10, what will C1 Gn get on? It will be 10n square. Now C1 Gn is 10n square, function fn is 10n square plus 10n plus 10. Now we know that the value of 10n square will always be smaller than the function for all values of n greater than equal to 0. So it means C1 Gn is acting as the lower bound for C1 equal to 10. Now, if I take C2 equal to 11, say for example 11 only I take, then it will be 11n square. The function is 10n square plus 10n plus 10. Now the value of 11n square will be smaller than the function of fn in the beginning. But at a particular point of n, the value will be, the value of n 11n square will get on to be greater than the function fn. Now you can calculate the value of n naught. Why so? Because I say that 11n square greater than 10n square plus 10n plus 10. Then what will the equation become? I will say that n square minus 10n minus 10 is greater than 0. So you shall compute the value of n. That will get on to be n naught, after which we could conclude that 11n square will be greater than this function fn. So we have proven that 10n square equal to plus 10n plus 10 is theta of n square. Now coming to the next example. In the next example, it is n square by 100 minus 9n. That is also equal to theta n square. Now if you have a look, it is n square is getting divided by 100 and then 9n is getting subtracted out of it. That is also theta of n square. Why so? I say that C1 Gn should act as lower bound and C2 Gn should act as upper bound. In this case, if I take C2 equal to 1, what will be C2? C2 and Gn, it will be 1n square. Now we know that the value of 1n square will be greater than this function fn for all values of n greater than equal to 0. So we can say the value of upper bound is being followed from 0 onwards itself. But for the lower bound, I say that the value of C will be very, very less. It will be lesser than 1. It will be, say for example, if I take 1 by 1000, because the condition is not required to be satisfied for every value of C. We say that there exists, because that is why we use existential quantifier. If you have a look at the definition above, it is existential quantifier. There exists a positive constant. Now, if I take C2 as lower bound as, for lower bound, I take C as 1 by 1000. Then Cn square will, Cgn will be 1 by 1000 n square. It is positive. 1 by 1000 also is positive. So there is existing a positive figure such that Cgn is coming out to be smaller than this function fn, that is n square by 100 minus 9. So there we have come across, we have found out the values of C such that for one C, it is Cgn is lower bound, and for the other C, it is acting as the upper bound. That is why we have proven that n square by 100 minus 9 is theta of n square. Now discussing the last example, that 3n cube, we cannot say that 3n cube is theta of n to the power 4. Why so? If you have a look, the degree of fn, that is 3n cube, is 3, while that of gn is 4. And we know that n to the power 4, the growth rate will be greater than that of n to the power 3. Even though it has been multiplied by the figure of 3, even then the rate of growth will be of n to the power 4 will be greater than that. Even if I take the value of C as small as 1 by 1000, that is 1 by 1000 into n to the power 4, but after a particular value of n, the value of Cgn, that is 1 by 1000 into n to the power 4, that will exceed 3n cube. So we can say that n to the power 4 cannot act as the lower bound of the function fn 3n cube, however small value of C we may take. Since it cannot act as the lower bound, that is why it does not satisfy the criteria for the theta notation. So it means 3n cube is not equal to theta of n to the power 4. Now the next notation, that is big O notation, we say that just reading out the definition. Big O of Gn equal to Fn such that there exists a positive constants C and N naught such that for all values of n greater than equal to 0, we have Fn less than equal to Cgn and both should be non-negative. If you have a look at the diagram, what is the scenario? There are only two curves in this. Unlike theta notation that had three curves, here there are only two curves. Why so? Because big O notation demands only the upper bound. It does not demand the lower bound. That is why the condition of big O notation is a subset of the conditions of the theta notation. That is why the set of values that are satisfying the theta notation, that will be a superset of the set of values satisfying the criteria of a theta notation. Big O notation, the set of criteria for big O will be a superset of that of theta. If you have a look at the diagram in the beginning, although the values of Fn, the graph of Fn and Cgn are crossing each other, but after a particular value of n, that is n naught, the value of Fn will always be smaller than Cgn. So Cgn is binding the function Fn from the upper end. So Cgn is acting as the upper bound of function f. So we say that since it is the set of functions that are satisfying the theta notation, that is a subset of the functions satisfying the criteria of a big O notation. That is why if, as written in the bottom, that if Fn equal to theta of Gn, then we can conclude that Fn equal to big O of Gn as well, though not vice versa. So theta of Gn, because it is a set, theta of Gn is a set of values. So theta of Gn is a subset of big O of Gn. Discussing the examples, I say that if there is any linear function a(n plus b), now a is any also particular value, constant value, b is also a constant value, I could say that it is big O of n also, it is big O of n square also. Why so? What do I demand? Because if it is a big O of n square, Gn is n square. What do I demand? What does the big O notation demand? It demands that the Cgn should act as the upper bound of function Fn. Now Gn is n square. So we know that values of n square will be greater than that of the linear function a(n plus b, though since b is getting added, if b is any particular positive figure, b is getting added. So in the beginning, the value of cn square might be smaller than that of function. If a is quite large positive value, b is also quite large positive value, then in the beginning, a(n plus b will always be greater. But if the values of n exceeds a particular point, after a particular point, the value of cn square will always exceed the value of this linear function. That is why we say, and cn square will act as the upper bound of the function a(n plus b after a particular value of n, that is n naught. So that is why, since it acts as the upper bound, that is why it satisfies the criteria for a big O notation. That is why the linear function is big O of n square. Now the same example that we discussed in the theta notation, that is 4n cube. It was not equal to theta n to the power 4, but it is big O of n to the power 4. Why so? Because big O notation demands only the upper bound, and n to the power 4, it satisfies the criteria of a upper bound. For values of n till 1 to 3, the values of n to the power 4 will be smaller than that of 4n cube, because 4 is the multiplication factor. But when it gets on to be n equal to 4, then the values of both functions, that is n to the power 4 and 4n cube, will be equal at n equal to 4. But after the value of n exceeds 4, then the value of 1 into n to the power 4 will always be greater than 4n cube. So if taking c equal to 1, n not equal to 4, the scenario, that is 4n cube equal to big O of n to the power 4, is getting satisfied. So hence it is proven that 4n cube equal to big O of n to the power 4. Now the third notation, that is omega notation. Like big O notation was, Gn was acting as the upper bound of Fn. In the similar fashion, for omega notation, Cgn is acting as the lower bound of the function Fn. If you have a look on the diagram, what is the scenario? That in the beginning, both Fn and Cgn are crossing each other, but after a particular value of n, that is a naught, the value of Cgn will always be lesser than Fn. So Cgn is acting as the lower bound of Fn. It will not let Fn to possess the value smaller than that after the particular value of n, that is n naught. Now the technical definition, if we read out, omega of Gn equal to Fn such that there exists the positive constants C and N naught such that for all values of n greater than equal to N naught, we have Cgn less than equal to Fn and both the values should be non-negative. Now, same as the relation was with the theta and big O, similar is the relation of theta and omega. That is, if Fn equal to theta of Gn, then we can conclude that Fn equal to omega of Gn as well. So, if Gn is a set of functions that are satisfying the criteria of theta notation, it will be a subset of the functions Gn that are satisfying the criteria of omega notation, because omega notation demands less than equal to criteria, while the theta notation demands only equal to criteria. Examples, if I say that there is a function that is 9n³ plus 12n square. Now, like in case of theta notation, the degree of Fn and Gn was supposed to be equal. The degree is supposed to be equal. It may be theta of n³ plus n square. It may be n³ plus n square plus n. Gn can be anything. It is not that there should be only one term polynomial in the theta notation, in any of the asymptotic notation. It could be multiple terms. But the degree, I'm talking about the degree. The degree of Fn and Gn should be same for the theta notation, for the theta relation to get established between the two functions. Similarly, for the big O notation, the degree of the function Gn should be greater than that of Fn. And in the similar fashion, the degree of Gn is supposed to be smaller than that of Fn if we have to want to establish the criteria of an omega notation. In this example, I say that the degree of the function 9n³ plus 12n square is 3. So what are the set of functions that satisfy the criteria of omega notation? All the polynomials which have the degree lesser than or equal to 3, all of them will satisfy the criteria of omega notation. So we can say that this function is omega of n to the power 3 also, omega of n to the power 2 also, omega of n to the power 1 also, and omega of n to the power 0 also. You can solve it. You can solve for different values of n, even if you take c equal to 1. That is 1n³, 1n square, 1n and 1. You can establish the values of n naught such that the values will act as Cgn will always be smaller than Fn. Rather, in this case, it will be the lower bound criteria will be satisfied for all values of n greater than equal to 0 in this case. Although it may be a little complicated, if I would have used minus 12n square, then the scenario might have been you might have to solve to find out the value of n naught. In this case, the n naught is 0 itself. In the last example, we say that Fn equal to omega of log n. We know that the rate of growth of the function log n is much smaller than the linear function. In this case, the linear function is 4n. Now, since the rate of growth of 4n is greater than the rate of growth of log n, so log n will be acting as the lower bound of the function 4n, however large value of c we may take. Although it is not required that for all values of c it should be satisfied, but for all values of c, this function log n will always get on to be smaller than 4n. If we take large value of c in the beginning, it may be large, but after a particular value of n naught, the value of c into log n will get on to be smaller than 4n. So since log n is acting as the lower bound of 4n, so what is the asymptotic notation between the same? 4n equal to omega of log n. Now, just all the three graphs have been drawn up one side or the other. I say that the leftmost is theta notation, that is the three graphs. Fn, C1Gn, C2Gn, Fn bounded from both ends by Fn. So Gn is the tight bound of Fn. In the central one, I say that Gn is supposed to be always greater than Fn. So Cgn is the upper bound of Fn. In the last one, I say that the Cgn is also always supposed to be smaller than Fn after n equal to n naught. So Cgn is the lower bound of Fn. Fn equal to omega of Gn. Now, if I say, as we have discussed earlier also, that if Fn equal to theta of Gn, then Fn will be big O of Gn also, and Fn equal to omega of Gn also. Why so? Because just analyze it, interpret it carefully, that Fn equal to theta of Gn, what does it say? That Cgn is acting as upper bound also, lower bound also. So If it is acting as upper bound, so we say that it is satisfying the criteria of big O notation. Similarly, if it is acting as a lower bound also, it means it is satisfying the criteria of a lower bound also. So it means Fn equal to big O of Gn as well, and Fn equal to omega of Gn as well. Vice versa is also correct. That is, if Fn equal to big O of Gn and Fn equal to omega of Gn, both conditions are satisfied, then we can say that Fn equal to theta of Gn as well. Equation you can interpret that if Gn is satisfying the criteria of Gn is a set of function that satisfies the criteria of big O notation, and Gn is a set of functions that is satisfying the criteria of omega notation. Then if we intersect them, then that will derive all the set of functions that will satisfy the criteria of a theta notation. So theta of Gn equal to big O of Gn intersection omega of Gn, because this is a set of functions. Now, discussing the complexity of some of the sorting algorithms, I could say that insertion sort takes theta of n square time in the worst case. So the time complexity is big O of n square. How it is coming up to be n square, that we shall discuss when we shall be discussing the sorting algos. But what I want to make you understand is that in the worst case means at most the maximum time that it will take to generate the sorted list of values. Since it is theta of n square in the worst case means maximum. Maximum means upper bound. Since it is upper bound, so which of the asymptotic notation is taken for the upper bound? That is big O. So if it is theta n square in the worst case, then it is big O of n square. Similarly, I say that this was the upper bound case. Now, if I take about the lower bound, I say that for each of the each of the values will have to be looked upon at least once if we have to sort the values. So it means at least once means that n will be the number of comparisons. N minus 1 rather. For example, in case of the best case scenario of insertion sort, if the values are already in the sorted order, then the first one will be compared with the second one will be compared with the first one, third one will be compared with the second one, fourth one will be compared with the third one, and so on till the last one gets compared with the second last one. So there are a total of n minus 1 comparisons. Since it is n minus 1 comparisons, what is, if I say that if the function is n minus 1, what is the asymptotic notation in terms of omega? It is n. Why omega? Because this is the lower bound. Lower bound means that the values cannot get on to be smaller than that. The number of comparisons that have to be executed in the sorting algorithm, that cannot be less than that. Since it cannot be less than n minus 1. So since n minus 1 is acting as the lower bound, so we say that the complexity is omega of n. Now coming up to merge sort, we say that in the best case also the complexity is n log n, in the worst case also the complexity is n log n, and in the average case also the complexity is n log n. So upper bound is also n log n, lower bound is also n log n. That is why in terms of asymptotic notations, we say that the complexity of merge sort is theta of n log n, because n log n is acting as both upper bound as well as lower bound. Now some of the properties of asymptotic notations, I say transitivity. Transitive, when is the relation said to be transitive? If A is related to B and B is related to C, then under both these conditions, if we can conclude that A will be related to C as well, then we say that the relation is transitive. Now in this case, we say that if Fn equal to theta of Gn and Gn equal to theta of Hn, then if both the criteria are satisfied, then we could conclude that Fn equal to theta of Hn as well. So we say that theta is transitive. If you analyze it logically, Fn equal to theta of Gn, it means Gn is acting as upper bound also and lower bound also of the function Fn. Similarly, and Gn equal to theta of Hn, it means Hn is acting as both upper bound as well as lower bound of Gn. Under both these scenarios, Hn will be acting as both upper as well as lower bound of Fn also. So it means Fn equal to theta of Hn. Similar is the scenario with big O. That is, if Gn is acting as the upper bound of Fn and Hn is acting as the upper bound of Gn, so it means Hn will be at the upper bound of Fn also. So it means in case of Gn, we say that tight bound will be established between F and H. In case of big O, we say that upper bound will also be established between F and H. And In the omega notation, we say that the lower bound will also be established between f and h under the two conditions, that fn equal to omega of gn and gn equal to omega of hn. So all the three notations are transitive. Coming to reflexive, when is the relation said to be reflexive? If every value is related to itself, then we say that the relation is reflexive. Say, for example, equality is a reflexive relation, while greater than is not a reflexive relation. But in case of theta notation, what is the scenario? We say that the degree of gn should be greater than, it should be equal to that of fn. So it means that each function itself also satisfies the criteria of theta notation for any function fn. So function fn is equal to theta of fn also. So fn theta is a reflexive relation. Similarly, fn equal to big O of fn also. Why so? In case of big O, what do we demand out of gn? We say that the cgn should be greater than equal to fn. Equality is also included. Since equality is also included, that is why we say that the function fn is also related to itself. It also satisfies the criteria for cgn to be fn equal to big O of gn. So since it is itself also satisfying the criteria, so it is related to itself also via the big O notation. That is why we say that the big O notation is reflexive. Similarly, omega notation that demands the lower bound. In that case, since cgn should be less than equal to, since it is equality is included, so function is related to itself also via omega notation. So omega is also reflexive. Now coming to symmetry, we say that fn equal to theta of gn if and only if gn equal to theta of fn. If you have a just interpret that if fn equal to theta of gn, what do you conclude about the, if it is a polynomial, what do you conclude about the degree? We can say that the degree of both fn and gn will be equal, only then the criteria of fn and equal to theta of gn will be established. Now since it is equal, if a equal to b, then b equal to a. That is why if fn equal to theta of gn, so gn will also be equal to theta of fn. This is called the symmetry. Now this symmetric relation is not followed by big O and omega. Why so? If a is less than equal, in case of big O, we say that cgn is supposed to be greater than equal to fn. So if a greater than equal to b, can we say that b greater than equal to a? No. So since greater than equal to is not following the criteria of a symmetry, so it means big O is not a symmetric, does not follow the relation to be symmetric. Similarly, omega is corresponding to less than equal to. Similarly, since big O is also not symmetric, in a similar fashion, omega also does not satisfy the criteria of a symmetric relation. So both big O and omega are not symmetric, only theta is symmetric because theta corresponds to equality in case of degree, if I say. Similarly, complementarity. Complementarity says that if fn equal to big O of gn, so we say that fn equal to big O of gn if gn equal to omega of fn. So that's all. We are left with the two other asymptotic notations, that is little o and little omega, that we shall cover in the next class. So thank you. So we say that fn equal to big O